They basically we call them the electrical potential. Now we have another term. This electrical potential is potential energy per charges. That we define by V. In which cases, in another term, this V we call potential energy. So with all this is gathering, then we have the following data. So we introduce you a V, we define it as a volt. So in that cases, we have delta V equal to delta U divided by Q sub 0, which case is minus A from A to B E dot ds. Okay, so here you go. So now we would like to find out the unit. What is the unit? And delta U is the energy in joules. And then this is charges. So delta V voltage is equal to joules. The unit wise, this is charges, in which cases is coulomb. So we define that this is called volt. The unit in voltage we call volt. So volt is equal to 1 joule per coulomb, right? The unit. So in general, you like to say that 1J divided by C. C stands for coulomb. So that is the basic about the electrical field, potential energy, and so forth. Now we will apply this to the uniform field. That means the electrical field, in which case it is potential, no changes. So we can anticipate that this is have a structure figure. Then using this to get into the next topic, in which case called the capacitor. So the next one they're talking about is related to the capacitors. Before they step in this, they want to say 20.2 is related with the potential difference in the uniform field. So potential difference in a uniform field. What does this related to? Is related with a gravitation field on the Earth's surface. For example, in a gravitational field, here is Earth. So here is a G. By the way, G is constant. So if all pointing in one direction. So now this is a gravitational field. Gravitational field close to Earth's surface is constant. Now we're looking at another field, in which case related with the electrical potential. How would you make the electrical potential in the uniform field? How would you provide uniform field? So this is a two electrical plane. They have charges like this. and they have these charges. If all these charges have the same value, then they have the electrical field in the uniform electrical field in there. So this is a very good concept, and that's again we using the voltage concept by doing this. In these cases, we like to say the electrical potential energy is like this. So we have something move from one place to another place. Typically, this is A, and then we move from A to B. So in this case, there's a different, there's a distance there, D. They have the same cases in here, move from one place to another place. So in these cases, there's a A here, there's a part B over here, then V sub B minus V sub A. In that cases, equal to delta V. In that cases, equal to minus electrical field from A to B of E dot ds. And that is the cases. Suppose the separation from this location to this location, the distance is d is constant, then you have a uniform field independent of the x, then you have E times d. E times d. So that's a voltage difference. And to conserve the data, the minus E to D. Okay, so the potential energy, delta U, potential energy is the potential energy, delta U, electrical potential energy, your Q sub 0 times electrical, this is called potential energy equal to Q sub 0 times delta V equal to minus Q sub 0 E times D. This is exactly we using the relationship calculating the capacitors. So we stop here today.